So good morning, everyone. My name is Rishabh Goyal, and today I'm going to present the work I did recently with my wonderful colleagues, which is called GLINKX, which is a scalable unified framework for homophilous and heterophilous graphs. So there's a lot of terminologies in this title itself. I'm going to unpack each part of it, and hopefully I'll be able to give a lot of intuitions to everyone who's come here. So before I dive into the method, let's start by defining what a graph is so that everyone is on the same page. A graph is a data structure that contains nodes and edges. So the bold black dots are edges, and the lines connecting them are called, black dots are nodes, and the lines connecting those nodes are called edges. Now, this begs the question, why do we care about learning on graphs? So graphs is one of the most ubiquitous data structures that exists in the real world. For instance, it exists in the form of knowledge. Like a knowledge graph is a graph that contains information about facts in the real world. For instance, Justin Trudeau is the Prime Minister of Canada, Barack Obama was the President of US, and me, myself, Rishabh Goyal, lives in Canada. So it's a graph that contains information about the real world. Another setting where you can have graphs is molecules. So a graph can be used to represent molecules, and you can do anything that you want to do with that graph. For instance, predict properties of that molecule. This is useful for settings where you synthesize a new drug, and you want to predict what properties does that molecule has. And last but not the least, social media networks. So all these social media platforms like Twitter, Instagram, TikTok can be represented as graphs, where the users are the nodes in the graph, and the edges represent the way different users interact with each other on the graph. For instance, in Facebook, one of the relationships that can exist between different people is called friendship, right? And on Twitter, it's follow, and on TikTok or YouTube, it can be subscription, like, or any other interaction that you do among different users on the platform. To give some intuition as to why leveraging this graph structure can be useful, let's consider an example of a social network like Facebook. Let's assume that I join Facebook and I make 10 friends on Facebook. Now, Facebook would like to give me content that is interesting to me. So for that, they want to say they want to know what my interests are. But since I just joined the platform, they don't have any information about me. So what they can do is that they can look at what my friends are, and if they have information about my friends, they can just approximate those interests as my interests, and then use that to serve content or run ads or whatever they want to do with that. Now, let's look at what are different tasks that you can do with graphs. So one of the tasks is called node level prediction. So in node level prediction, you're given the entire graph and you want to do something about each and every node in the graph. An example would be the example that I just gave, where you want to predict interests of a node in the network. The second type of task that you can do on a graph is a graph level prediction task, where you want to make a prediction about the graph as a whole. So an example for that would be predicting properties of a molecule. Like you synthesize a new molecule, now you want to know what is it useful, what is this molecule useful for? And the third type of task that you can do on a graph is edge level prediction. The most important application of this sort of task is in recommendation systems. So you can consider a graph of users and items, and then predicting an edge, whether an edge exists between a user and an item, translates to saying whether an item should be recommended to that person or not. But in this work, or like for this presentation, we're going to only deal with node level prediction tasks. Now, GNNs, or also known as graph neural networks, is one of the popular classes of methods that have been used to deal with node level prediction tasks. So now I'm going to give a quick primer on what GNNs are and some of the shortcomings, and we'll take it from there, what we propose that is better than GNNs, or like competitive to GNNs. In GNNs, there are 3 steps, essentially. The first step is you pick a node for which you want to make a prediction. In this case, it's in this case, it's the central red node, and then you sample a neighborhood around that node. So in this case, we are sampling 2-hop neighborhoods. So what is a 2-hop neighborhood? So you go 2 hops from the node that you care about. So the nodes that are connected to the central node are the first hop neighbors, and the neighbors of neighbors is the second hop neighbors. So in this case, we sample 2 hop neighbors. And then once we have sampled the neighborhood, what we do is that aggregate information from all the neighbors that we have. So the second step, the green nodes send information to the blue nodes. The blue nodes aggregate that information and then send it to the red node, finally. And then the red node aggregates that information and uses its own features to make a prediction about the node itself. So these are the 3 steps that a GNN does. Now let's see how would we go about doing that for this graph. Let's consider target node A, and for target node A, the second order, first order, and the target node, something would look like this. Like this is like the computation graph for target node A. Now one can easily see that the second hop neighbors, they can explode a lot. Like there can be a lot of second hop neighbors, and you need to process all those neighbors just to get representation for A, right? And this becomes even more impractical, where if you are connected to a hotspot node. A hotspot node is a node that is connected to everyone in the graph. So if you have to process everyone in the graph just to get representation for a single node, it's not really practical for a real world setting, especially for networks like Facebook, Instagram, or Twitter, right? Because they have billions of nodes, and you want to make predictions very fast. Usually you want to make predictions in order of milliseconds. So processing order n nodes, where n is in the order of millions or billions, is not practical enough. So an easy thing to do is to just say that I'm going to sample my neighborhood, right? I'm going to always sample 5 nodes and just going to make prediction about that. But the problem with that is that now you're sampling from order n nodes again. So sampling also takes a lot of time. So which can be impractical as well, because at least it's going to take you order n time to do that. So it's not really practical for the real world. So Google Dataflow has a solution to handle such large graphs, but I haven't checked it out. If someone is interested, they can do that. But there's an issue with that. The problem is that the technology that Google provides may not be really compatible with the infrastructure you have, right? And the ROI of trying this and seeing how much boost you get over the baselines or whatever your current system in production is, it may just not be worth it. So when we were working on this problem, we thought about, we don't want to bring in any new infrastructure, because if you have tried to integrate a new infrastructure in your company, you would know it's a big pain. It's just not possible, and probably sometimes the ROI is not really worth it, right? So we said that we want to build something in-house that is good enough with the infrastructure that we have. So, and then we decided to have certain goals that we would like to, achieve by end of like when we get the method, we want to achieve certain goals. So one of those goals was to get a node classification method that works on both homophilous and heterophilous graphs. Now, what is a homophilous graph? On the right is on the left is an example of homophilous graphs. So a homophilous graph is a graph where the 2 connected nodes have the same color. So you can see on the left, the central node is connected to other nodes that have similar color, right? And the heterophilous graphs are graphs where it is the opposite. The connected nodes do not have the same color. So the graph on the right, the central node is not connected to any node with the same color. So these are extreme settings that can exist in your graph. But we want a method that will work on both the graphs without you knowing that there is heterophily or homophily in the graph. And the reason for that is this homophily and heterophily are not binary constructs. So a graph can have homophily and heterophily in different parts of the graph. So you want a method that works for both. So this graph just shows you a distribution of homophily within a single graph. So on the 0 side, it's heterophily, and on the 1 side, it's homophily. So there's a distribution of homophily in a graph. So you want a method that can work on both the settings. Our second goal was to work with dynamic graphs or static graphs. So transductive setting is a setting where your graph is static, and your inductive setting is a setting where the graph can change. So why the inductive setting is a more practical setting, because if I have a social network, it's going to change every day. I have like hundreds of accounts that are getting created every day. So I want something that can deal with that ever-growing node and edge count every day. And the third goal was that we wanted to be scalable and simple. So for that, we said we want to work at the node level. So when we looked at the problems in GNN, it was about sampling the neighborhood and then passing messages from second hop neighbor to first hop and so on and so forth. So that's about like message passing. That was sort of a bottleneck, computational bottleneck that made things impractical. So we wanted to make sure that we are at the node level. We don't have to deal with edges at all during the training process. And if we have to do that, we do it in an offline fashion, meaning that it doesn't happen during the training process. And even if we do that, then also we only pass very small messages along the edges, because the size of the message that you pass over the edges sort of is expensive as well, where in GNNs, the size of that embedding is very large, or like the size of message that you pass is very large, so you don't want to have that. And we decided to make the dimensionality of that message to be of the size of the classes. And I'll talk about why that is the case in a bit. Now, with these goals in mind, we came up with a method that helps us achieve all these goals and can still be competitive with GNNs that we started with. So the method is called GLINKX. It has 3 components, which I'll go into the details now. The first part is monophilous label propagation. So monophilous labels propagation takes inspiration from monophily. So I talked about homophily and heterophily before. This another term called monophily, which means that connecting to a unique friend. So if we consider the figure on the slide, so one can see that a lot of the green nodes are connected to node I. So now let's say if I want to make a prediction about J3, then without giving me any information, I can say that the color of J3 is more likely to be green than any other color, because a lot of the green color nodes are connected to node I. Now, node I can be anything. It can have any color. It doesn't really matter. So this is the sort of intuition that we try to bake into the model by just passing in the second order label information. In this case, the second order label information is basically saying for J3, I have 2 nodes with green color, 1 node with blue color, and 1 node with orange color in my second order neighborhood. So I'm just going to take that and then use it as a feature. And now, remember one of the goals that we started with was to have a method that works for both heterophilous and homophilous settings. So these pictures present settings for both homophily and heterophily. This shows that like this method has a potential to work in both the settings. The left side is a heterophilous setting where the nodes connected don't have the same label, whereas on the right, the nodes have the same label. So this sort of structure can exist in both the settings, so hence it can work in both the settings. And another thing is that it's very scalable. It's just a second order information that we are trying to get. The second part is the positional embeddings. So people who have worked in NLP, they would know that positional embeddings have been pretty common in NLP models. So the motivation of using a positional embedding is the same, but there is an inherent objective, or like there's an implicit assumption that this is very scalable, because the number of nodes in a graph can go to billions, and the number of edges can be of the order of trillions. Processing that information, it's a lot. It's a lot of work. So you want methods that can do that fast, and they are simple to maintain, so that you don't have to hire an entire team of engineers to just maintain this one system. You don't want to do that. It's expensive, and it's not really practical, and the ROI, according to me, is not worth it. And the third part is just the node features. These are essentially the node features that you would have attached to the nodes in the graph. Like, for instance, if your graph is a Wikipedia graph and you're trying to make predictions about what is the topic of that article, an example of node features would be just looking at the content of that article and then embedding it using some method. It can be TF-IDF, transformer, or whatever your favorite methodology is. Now I presented these 3 methods. Now let's see what makes GLINKX scalable and it can work for an industry scale graph. So first one is the monophilous label propagation part. So monophilous label propagation, as I said before, it essentially collects the second order label information. Since it just collects the second order information, you can write a map reduce job, which a lot of the companies have, and it's a pretty mature technology. If you're dealing with huge amounts of data, then most likely you have a version of MapReduce in your company. So it is just a MapReduce job that you can have. The positional embeddings, so there's a PyTorch library called BigGraph that lets you embed your entire graph, which is order of millions or even billions. I've seen graphs getting embedded of that order as well, that can embed them pretty fast. I mean, within a matter of a day or even less than a day, depending upon how much resources that you put in. And the third part was node embeddings. So there is no work that you need to do for that because they are already there on the nodes. So there is no work to get that. Obviously, if you're embedding it in certain way, then yes, there is some work, but usually they are available out of the box. So now with these three components, you don't have to deal with edges anymore when you train. So you can just use mini batch training, which if you're using machine learning in a company, that's supported well usually. Mini batch training means that you just sample IID, sample from your data set, and just train your model on that. And as I said, like there's no need to do any neighborhood sampling. And what we did at least is a very simple thing, just to concatenate all these three components and then pass it through a model and then make a prediction for the node model. And this is like the simplest model that you can have, and it's very easy to maintain, and you can scale it as much as you want. You can put how much ever parameters in your model as you want, or you can put a logistic regression or whatever you care about. It's very easy to maintain. Now, let's look at some of the experimental results. How does it compare to other methods that exist? So we did experiments on both homophilous and heterophilous data sets. So the box in the red are our method. The box in the green is a graph-based method. And the box in the orange is a method that's that's a very simple method, and it has been used for heterophilous data sets. You can see that our method is a lot better than a graph-based method if we are given the same budget. So, and as we shift from homophilous to heterophilous data set, the performance still is competitive with whatever the baseline or whatever the method is used in for that particular regime. So when I say regime, I mean heterophilous or homophilous regime. And the GNNs are known to not work for heterophilous settings, so that there's a not applicable there. So they're definitely worse than our method. But the other baselines, the one in the orange, you can see that as we even go from heterophilous to homophilous regime, our method is still competitive. So, and it's way less expensive. Like it's not a lot compute intensive as well. Now, finally, we did some ablation analysis to see whether all these three components are adding any value to the system or not. So we ablated each component one at a time, and then saw that if you remove even a single component, you lose on the performance. Just ignore what stages here mean. Like that's an implementation detail that we went about implementing our method into. So just probably ignore that. But I think the take-home message from here is that every component contributes to the performance, model performance. Now, some future work that we have in mind is like we just looked at the second hop neighbor label information. Now you could look at first hop, third hop, n hop neighbor information as well. So we have only used one component of the graph, which is the second hop neighbor information. Future work is to see if we can add other sources of information as well in a scalable way. Again, you don't want to aggregate everything else just without thinking. So that's one future work we have. Use higher order statistics. So what this essentially here means is that, so when we got the information from my second order neighbors, I just counted. Right? I can build more complex functions instead of just counting. So that's what second future work means. It is an implementation detail which I have not talked about. So probably it's not that intuitive here. But the third future work is inductive setting. So I mentioned in the beginning that we want a method that's inductive. That is that it works on dynamic graphs. So our method, because of one of the components in the positional embeddings, is not inductive. And I can explain a bit why that is the case offline, but there are ways of making that method inductive. So we're gonna try that. And then finally running it on bigger data sets. The data sets we considered are not that big. They don't go to billions of nodes and edges. So we would like to test it out on graphs of that size. And then finally, there's a huge product impact there for any application where you can make a node level prediction. For instance, user interest prediction. You can, if you want to predict what are the interests of the user, you can use it to predict demographics of the user as well, if you're interested, depending upon whether that's allowed in your company or not, because it can be, it may not be legal or whatever the constraints that you have within the company. Another application is the spam detection, because let's consider social network again. If you want to make a prediction whether a certain node is spam or like they're spamming the entire network or not, that's another application that can be, that this method can be applied to. And finally, I would like to thank everyone for listening to me. Hopefully, I was able to give some intuitions about our method. And this work is on archive if someone wants it. And you can scan the QR code as well. And if you have any questions, I'll be happy to take them offline. And you can reach out to me on Twitter or LinkedIn. I'll be happy to answer any questions and point to any resources that you may want to look at as well. Thanks again.